All right, let's talk a little bit about uncertainty propagation. And if you wanted to look a little bit deeper into this topic, section 3.10 on the book is pretty good. I'm sure there's a lot of information out there in addition to that on the internet. So if we can recap about where we are right now in the course, we have figured out a way to identify and quantify the uncertainty associated with a measurement, or in other words, how much error can we expect to be in our measurement? Because almost nothing can we measure exactly with 100% precision. And so there's going to be some error involved in our measurement due to several variables. We've talked in length about the different sources of error and how do we quantify how certain we are with our measurement, or identified the uncertainty associated with our measurement. We've got our bias and our precision. So our bias is something that typically will move us off of the true value on a repeatable basis. And so therefore we can do post-processing and subtract it off, or we can calibrate it. There's a lot of ways that we can fix our bias. Or worst case, we can just quantify our bias and add it in with our precision uncertainty. Now switching over to our precision uncertainty, again, that is taking multiple samples. So like measuring the thickness of a brick that is uneven on the surface. If you measured just once, you probably would have a significant amount of uncertainty because you captured one data point on the thickness. But if you did multiple measurements, now you can calculate a mean and a standard deviation of those measurements. Or another example we had in the class was pulling marbles out of a bag and measuring the diameter of the sphere and then doing it on another marble and another marble. And you take multiple measurements, now you have a mean and a standard deviation, and you can combine that with our confidence interval, which is defined by the area under a Gaussian distribution curve. And we set that by setting how many standard deviations away from the mean we want to capture the area under the curve, which is our confidence. And the distance between our mean and that point, or that barrier that we're setting up with our z-score value, is our confidence. So the area under the curve is our confidence or probability of capturing a data point. So if we look at that, we've done that so far for a specific variable. But what do we do when we have multiple variables that are combined in a governing equation? So that's what our uncertainty propagation conversation is today, is how do you deal with the uncertainty associated with each individual variable, whether it be how sensitive that variable is because it is maybe to the second power or third power in the equation, or maybe because the instrument we chose to measure that variable is very insensitive or maybe is inaccurate. And so uncertainty propagation, what is the uncertainty associated with the variable that comes out of a governing equation based on measuring each individual quantity that rolls up into that governing equation? Okay, so here is the example problem that I have chosen to help us get thinking along these lines. We've been tasked to measure an air mass flow rate in a large duct using a turbine anemometer. So a turbine anemometer, that's going to give us one of the variables, which is our wind velocity or our air velocity. So what about the other variables that make up the governing equation for mass flow rate? Well, we've got density and we've got cross-sectional area. So if you think about it, we have multiple sources of error because of multiple variables being measured. So that density, maybe somebody put that together in a table. Maybe they gave us that uncertainty associated with their variable. Or maybe we can assume it's 95% confidence interval based on the fact that it is an engineering related variable. And then the area, well, we took out a tape measure or some other measuring device and we measured the cross-sectional area. So how does the uncertainty associated with that roll up into our overall mass airflow meter? And then we've got our mass airflow calculation. We also have our turbine anemometer. There's probably some bias and precision and uncertainty associated with the measurements we're doing there as well. So how do you bring all those together and report a total uncertainty from all sources of error for the mass airflow rate. That's what this discussion is about. So uncertainty propagation. How do we estimate the total uncertainty when we have multiple independent sources of error present? Well, it's really important that they are independent of one another. So that's probably the first thing we need to think about, is having them be independent of one another. Thus far, we've talked about the uncertainty with regards to confidence interval and confidence of a single measurement. So now we're taking it beyond that into a governing equation. If we wanted to determine the size of a rectangular prism, for example, length, width, height, they're going to each have their own uncertainty associated with them, especially if we use different measuring devices for each one of those. So what if somebody asks us, what is the total uncertainty associated with that volume? Well, we'd like to answer that with respect to the volume, not each individual variable. So how do we define the uncertainty? Well, we've got this precision uncertainty variable shown here, P sub x. That's the precision uncertainty of this variable x. And like we've seen before, we've got our z value here, which is dictated by our confidence that we select. And we have this divided by 2 because the table that we use shows half of the distribution, or half of the area under the curve, table 3.2. And so that's why we have this confidence divided by 2, so we can utilize that, that table. And so our z value times our standard deviation. So our z times our standard deviation is what is giving us our uncertainty for precision. Now we have, instead of our sigma in here, our standard deviation, we have our S sub x, which is the standard deviation of the population, divided by square root of n, which is the number of measurements. And so you can see right here, we are using the central limit theorem in this specific instance. And this is probably the most common instance that we are going to use in this class, because we need to use the central limit theorem very often. So let's assume for a minute we've got measuring something like the length of a rod, or like this box that we've got on here. We've got the length of something and we want to measure it with a 95% confidence or probability. So we'd have something like this, where we've got our mu plus or minus our 1.96, which is related to the number of standard deviations. So this is our z value for our 95% confidence. And then we have our standard deviation. So what if we wanted to measure the length of two objects? Maybe we have a bin full of this type of object and a bin full of this type of object, and we want to measure the overall length. Can we just take 2 times mu plus or minus 2 times our 1.96 sigma? No, we can't, because it's going to be something a little bit lower than our 1.96 sigma times our 2, because we have 2 samples in here. And why is that? Well, it's because we are combining 2 different distributions. And so we can't just add these two distributions together, because they may look a little bit different. Maybe we have a distribution that looks like this, and we're trying to add a distribution that looks like this. So what would cause us to have different distributions? Again, it could be the device that we chose to measure variable A and the device that we chose to measure variable B. Maybe we've got micrometers to measure this one, and we got a tape measure to measure this one. And so those are going to have different distributions associated with them, so we can't just combine them. And so what are we going to do? How are we going to combine these distributions? And again, we're talking about our precision uncertainty here. Well, let's start with the governing equation. So we have a governing equation here, F, with these variables that make up that equation, that governing equation F. And so if we take that and we say, well, each one of the variables that makes up that function have been experimentally determined, which means we've measured them multiple times, or we've measured them with different devices. We are going to take those variables and we're going to see how those variables interact with one another. We need to make sure that we need to understand that each of these variables have some uncertainty associated with them. So again, maybe it's a bias, maybe it's a precision, but there is some uncertainty associated with measuring that variable. So if we take that governing equation and we differentiate it with respect to our uncertainty here, what are we doing? Well, we're trying to find out how sensitive each individual variable in that governing equation is to our uncertainty. So if we take the partial of our function with respect to x, now we have this partial of x with respect to u. We do that for each one of the variables. And so this is kind of what this total equation is going to look like. We go out through all the variables in the governing equation. Now, if we multiply our governing equation by du, now we have our function, the differential of our function is now the partial of our function with respect to x, and we have this dx and our dy all the way up to the end variable dn. So what does the dx and the dy represent? Well, if the dx du represents the instantaneous change, I mean, that's what the partial is, right? Is the instantaneous change of a variable with respect to our uncertainty. So how much does it change? So it's kind of the sensitivity of that variable with respect to or the sensitivity of our uncertainty with respect to that variable. Then the dx is the total change. That's kind of handy because if we see this dx here, that's the total change. That is our uncertainty for that specific variable. So maybe that is the uncertainty given to us by the manufacturer. Maybe this is the uncertainty given to us by the manufacturer of another measurement device. So if we combine these, now we have a mean and a standard deviation that we can use in this equation right here. Okay, so what about negative uncertainty values? Well, we already know the answer. We're going to use root sum squared. And so if we take this equation and we use root sum squared, then what happens to all of the different variables that go into? We end up with this equation here. If we square all over the terms, we end up with this equation, but then we also have these cross terms. This gets pretty messy for us. Is there any assumption that we can make to simplify this calculation? Obviously, yes, because that's why it's in the slides here. That's why we're talking about it. Is if we make one assumption, we can get rid of all these cross terms and we end up with this nice clean equation right here, which is pretty easy for us to deal with. So if we assume that each error source is random, and again, like we talked about at the very beginning, is independent of one another, then our cross terms sum to zero, leaving us only with these square terms. So let's think about, what does this mean that our sources are random? That means we have the same probability of getting one answer or the other answer. That, and then independent of one another means that if we go back to our mass flow rate equation, that the uncertainty related to the cross-sectional area is independent of the uncertainty related to our velocity. Now, very often that's the case, not every single time. So there's going to be times that if you are doing fundamental research where you can't ignore or you can't employ this assumption and have those cross terms go away. You'll have to actually deal with those cross terms. But for the most part, as long as those error sources are random and independent of one another, those cross terms go to zero. And so this equation right here is what's shown in the text, equation 3.33. We use this equation all the time, and we've got it in this little bit different format, equation 3.35. So here is the uncertainty with respect to y of each of these different variables that go into here. And so we're going to use this all of the time. So if this y is our governing equation, we have each individual variable going into that equation, and we have a certain amount of uncertainty there. And then we have the partial differential equation of our governing equation y with respect to the first variable, our governing equation y with respect to our second, all the way to the end variable, and then how much change is there or how much uncertainty is there for each of those variables. So if we look at that, well, now the uncertainty of each of these variables, so this u sub n is just our standard deviation of that one variable times our confidence interval. So here's our uncertainty. That's pretty cool. Now that we can just plug this in for each of these variables, now we can calculate out what our uncertainty is relative to the overall governing equation. So one other note that's very important is the confidence interval, the confidence level, whether it be 95 or 99, 99 or 95% confidence level must be the same for all variables. And so if they're not, so maybe you have, instead of this confidence for this specific number 2 variable, maybe that's at 99 and the rest are at 95. We need to use the table to convert that over to a 99% or 95. So all of these variables are the same. So then you can report your overall uncertainty for this governing equation at one confidence interval. Okay, so here are some uncertainty propagation assumptions that we're making. We assume that the uncertainty behaves similar to the sample deviations. We also assume that our first order Taylor series expansion to the sensitivity is an acceptable approximation. So we've got the Taylor series expansion, and we say that each variable has a sensitivity. Typically, this is a pretty good assumption, but we need to make sure that that is a good assumption. We also assume that our deviations are small relative to the values being measured and the changes being experienced. So our deviations are small relative to the values being measured. So that means if we have a deviation that is almost the same size as the variable that we're measuring, then this is no longer a great method for propagating all the errors through. So just as a reminder, we've got our sigma here, which is the population standard deviation, and we have our capital S, which is the the sample standard deviation. So we've got n minus 1 because we have 1 degree of freedom removed